Hi again. We're going to solve a second order circuit again for VC of t this time. And so remember the table, well, first off, so you can only use the S domain, the method that we've been doing, only when you have initial conditions that are 0. So in this case with this circuit, you're not going to have 0 initial conditions. So there are ways to compensate for that, which is beyond the scope of this class. So for now, we're going to use the table that already went through the solutions to be able to solve this. So with that, we need to determine, are we parallel or series? Again, the final state of the circuit, which is going to be when it's closed, it's going to show us that yes, we have these are in parallel to each other. And so we have a parallel form. Again, you look at the capacitor and inductor in relationship to each other. So they are in a parallel configuration, so we have parallel. So to determine which characteristic we have, critically damped, underdamped, or overdamped, we need to find alpha and omega naught. So alpha for a parallel form is 1 over 2 times RTC, R Thevenin times C, and omega naught is 1 over the square root of LC. So taking that, we have to find the Thevenin resistance equivalent, and so again, final state, so t equals 0 infinity. And so the switch will be closed in that case, and then we have these two are in parallel. So just remember in series, you just have on both sides of them is what you're finding. So you just have them in series and then you find the A on the top and the bottom of those. So in this case, we have A and B, then we need to remove the sources. So removing a current source leaves it open. So this will become an open, and removing a voltage source becomes a wire. So then we're going to take our pathway from the A side back to the B side. We see that we go in two opposite directions. So we have a parallel form and we have two directions. So that means there's going to be two components. So on the left side one, you can hopefully see that those are in series. So you have 9 ohms. And then on the right side, which will be parallel then with 2. So when you take these pathways, you're just looking for whenever you go into two different directions as a parallel. Whenever you keep going through something, it's a plus. So you can see that you go 6 and then plus the 3. So that's going to be added together to give you that 9. So combining these, you end up with 9 in parallel with 2. And that gives us 1 over 1 over 9 plus 1 over 2. And then we get, combining those, you get 11 over 9 times 2, which is 18. So you get 18 over 11. So that will be our RTH. So we can plug that in here now, and we get 1 over 2 times 18 over 11. And then this was 0.5, and then 10 to the minus 3 is 0.5 milli, so 10 to the minus 3. And this gives us 611.1. Again, these are meters per second is the units for the alpha. And then this is going to be 1 over the square root of 6 milli times 0.5 times 10 to the minus 3. And this is going to give us 577.35. And this is in radians per second because it's omega. So we can see here that we do have that alpha is greater than omega naught, which is our condition for underdamped. Overdamped. was like, that's not underdamped, overdamped. You find overdamped. So alpha is greater than omega naught. Copied the wrong one there. Okay, so overdamped is our condition here. So here we now need to find our A1, our A2, and our initial IL0, IL infinity, and VL0. So from that, S1 and S2 are found from the alphas and omega naught. So S1 is going to be minus alpha plus the square root of alpha squared minus omega naught squared. And that gives us minus 411 meters per second. And S2 is a minus alpha minus the square root of alpha squared minus omega naught squared. And that gives us a value of minus 811 meters per second. And then we need to find the initial values. So going to time 0 minus, the switch is open. These have sat for a long time, so open for the capacitor and a wire for the inductor. And so to find IL of 0 minus, we can then see that it's going to be in the same current that's going through the 6 ohms is going to go through the IL. Again, there's no current here because it's a dangling wire. If we ground this, then we can either find the voltage at this node by doing a summation of the currents in each of those 3 branches, or we can notice that it's a current divider and that IL then is going to be 6 times 3 over 3 plus 6, which is 9. So 18 over 9 gives us 2 amps for this initial value. So at t equals 0 plus, you're going to have this current source, the direction going down of 2 amps, and a voltage source. So IL of 0 will stay the same, 2 amps, and VL of 0 is in parallel to this VC, which is going to be also 0. So our last stage is infinity. And in this case, we have the circuit is closed. And again, these have sat there a long time. And we have this turns into a wire. So IL now, we have current coming from the 6 and we have current coming from this side. So the current coming from this side is going to be, it's a minus 12 over on this one. So we can do a minus 12, and again grounding this will be 0, minus 0 over 2 gives us a minus 6 amps. And then we have the same thing on this left side is again a current divider because this is ground, 0 volts here. So that does still divide the same way as a current divider. So this is 2 amps due to the same reasoning as above. And so coming into IL, I have IL going out and 2 coming in and minus 6 coming in. And so this gives me a minus 4 amps. So this will be my final value for IL. So going back to this, we had VL of 0 was 0. This was 2, I think. Yep, 2 amps for the initial. And then this one was a minus 4 and a minus 4. So plugging these in now, we can say that IL of t actually, I'm going to go backwards and do A1 first. So A1 is going to be a minus S2, which is minus 811. And then we have 2 minus a minus 4 all over S1, which is minus 411, and then a minus 811. And same method on A2, we have minus 411, and then 2 minus a minus 4, and then minus 811 minus a minus 411. And so we get A1 to be 12.15, and A2 is a minus 6.15. And so IL of t is A1 12.15 e to the S1t, so minus 411t, minus 6.15 e, so that's A2, e to the S2t, plus IL infinity, which was a minus 4. So this is our IL of t for t greater than or equal to 0. So now to get VC of t, we note that VC of t is equal to VL of t because they're in parallel. And we know that VL is equal to L dIL dt. So we need to differentiate that. So differentiating DIL dt and taking L times that, we get 6 times 10 to the minus 3. And then differentiating the minus 4 is 0, and we get 12.15, and then we bring down the 4, minus 411. And then we bring down the minus 811. And we multiply this out, and this gives us VC of t is going to be 29.95, and then e to the minus 811t minus e to the minus 411t in volts. And this is our answer for VC of t. All right, thank you for watching.